what can comets reveal about the origins and future of our solar system?
Well, that is really the ultimate question in planetary science.
And
Because on one hand, these objects are incredibly valuable time capsules. They preserve the original dust in the ice, the raw molecular ingredients that were just swirling around when our solar system was forming. And
4.5 billion years ago.
exactly. But here is the central tension we really have to wrestle with today. They are not pristine time capsules.
Yeah, they aren't just sitting in a cosmic museum vault somewhere.
No, not at all. They aren't sealed under glass. Every single time they swing near the sun, that ancient record is being continually altered. You've got intense solar heating, you have physical impacts, violent outgassing, solar wind erosion. I mean, they are constantly editing their own history.
So it's like an edited archive.
Yes, an edited archive. And to read that archive, you have to peel back layer upon layer of history and solar alteration.
Which is exactly our mission in this deep dive today.
Right.
So we're exploring the foundational ideas laid out in Carl Sagan and Druyan's phenomenal book, Comet. But we're updating their canonical work with the absolute latest planetary science.
Mm-hmm.
Today, we'll trace how humanity went from literally fearing comets to calculating their orbits. We'll dissect the actual anatomy of an active comet. We're going to examine the spacecraft missions that brought us face-to-face with these icy dirt balls, unpack the intense scientific debate over whether they delivered Earth water and organics, and finally, look at the real science of comet impacts and planetary defense.
It's a massive journey, really, and I think it requires us to confront this staggeringly beautiful visual paradox.
Oh, the scale of it. It totally breaks your brain because you have this tiny dark nucleus, right?
Yeah, maybe just a few kilometers wide, like the size of a small town.
Right, a small town. And when it gets close to the sun, it generates this luminous cloud of gas and dust that can physically grow larger than the planet Jupiter.
It's wild.
A tiny, pitch-black speck lighting up millions of kilometers of space.
And what's so fascinating about that physical paradox is how it completely mirrors the historical one. For most of human history, that massive glowing apparition in the sky was profoundly misunderstood.
Well, let's unpack that history, actually, because the shift in human understanding is just fascinating. For centuries, comets were universally seen as omens.
Right.
And you really can't blame early civilizations for that interpretation. I mean, if you think about the natural cosmic order, the sun, the moon, the planets, they move with this comforting, predictable regularity.
They follow the rules.
Exactly. They follow the rules. And then, out of nowhere, this glowing sword appears in the sky. It changes shape, it moves against the background of the stars, and then it just fades away.
And without a physical, mathematical model to explain it, human beings they naturally impose meaning on the unknown. So a comet was interpreted as a signal of danger or, a royal death or some great societal transformation.
Yeah, because they needed a reason for it.
Right. It wasn't that these early observers were foolish. They were just trying to find a mechanism for something that seemed entirely random and chaotic in an otherwise very orderly sky.
So the pivot to physical astronomy changes everything. And really the turning point there is Tycho Brahe in the late 1500s.
Yes.
He observes the Great Comet of 1577, and instead of just wondering what it means, he decides to measure exactly where it is.
Which was revolutionary.
Yeah, he uses parallax, basically measuring the comet's position against the background stars from different locations in Europe. And the math proves the comet is much further away than the moon.
Which is a conceptual earthquake.
Totally.
Because prior to that, the prevailing Aristotelian view was that comets were just weird atmospheric phenomena, like glowing swamp gas trapped in our own sky.
Oh, wow, swamp gas.
Yeah, literally in the atmosphere. So Brahe shattered that idea of crystalline celestial spheres. He proved comets were actually moving through the planetary realm.
And that sets the stage for Isaac Newton. Newton publishes the Principia, applying his universal laws of gravity to show that comets are physical bodies moving through space on elliptical orbits.
Right. They aren't just random flashes of light. They have paths.
Exactly. Which in turn gives Edmund Halley the mathematical tools to look at historical records, crunch the orbital parameters, and predict that a specific comet would return.
And when it did return in 1758, exactly as the Newtonian framework predicted, it completely rewired human thought. Science didn't remove the wonder of comets. It replaced those imposed mythological meanings with something infinitely more incredible. Discoverable, testable relationships of gravity and time.
We turned a terrifying anomaly into a lawful part of our neighborhood.
Beautifully put, yes.
And the natural progression of that is once you can calculate the orbit, once you know exactly where a comet is going, you can start to figure out what it's actually made of. So let's physically dissect one.
Let's do it.
Let's talk about the anatomy of an active comet. Because for a long time, the public imagination held onto this idea of a dirty snowball, like a packed ball of ice with some grit in it.
Right, the Fred Whipple model. And that was a very useful early model. But icy dirt ball is a much more accurate description based on modern science.
Okay, icy dirt ball. Why the shift?
Well, the nucleus is highly porous. It has a very low density. In fact, if you could find an ocean big enough, some of them would actually float.
Wait, really? They would float?
Yeah, they are that porous. It's this incredibly dark mix of refractory grains. Basically rock, silicate dust, and complex carbon bound together by volatile compounds like water ice, carbon dioxide, and carbon monoxide.
So it's not mostly ice, it's mostly dirt and rock held together by ice.
Exactly. And the surface isn't a smooth, uniform sphere at all. We are talking about towering cliffs, deep fractures, sinkholes, and massive boulders. It's highly irregular.
So the magic really happens when that dark, highly irregular dirt ball falls toward the inner solar system. Because solar heat penetrates the surface, and those volatile ices undergo sublimation.
Right.
And because they are in the vacuum of space, they transition directly from a solid ice into a gas, skipping the liquid phase entirely.
That escaping gas expands rapidly, and as it does, it drags the dust grains right off the surface. But because the topography is so uneven and chaotic, with those cliffs and sinkholes, this outgassing doesn't happen uniformly.
It's not like a gentle mist everywhere.
No. It shoots out in these violent, highly concentrated jets from specific vents on the surface. That expanding envelope of gas and dust creates the coma, which is that massive temporary atmosphere we see illuminated from Earth.
Which brings us to the most famous visual feature, the tail. And I want to explicitly correct a massive misconception here because it is so pervasive.
Oh, the wake misconception.
Yes, most people look at a comet and assume the tail just trails behind it like a wake behind a speedboat, simply showing the direction the comet just came from.
Right. It is entirely intuitive to think that, and it is entirely wrong physically.
Yeah. A comet actually has two distinct tails, and neither of them acts like a wake. First, you have the dust tail. This is made of solid macroscopic particles, and it gets pushed into a broad, curved shape by the literal pressure of sunlight.
Yes.
Which is a wild concept, honestly. Photons of light have no mass.
But they have momentum.
Exactly. And that solar radiation pressure literally batters the dust grains away from the coma. Then you have the ion tail. This is made of charged, ionized gas particles, and it gets caught up in the solar wind and the sun's magnetic field, shooting incredibly straight.
The overarching physical rule here is that both of these tails are governed by forces coming entirely from the sun.
Right.
Because they're being pushed by sunlight and solar wind, the tails generally point away from the sun, regardless of which direction the comet is actually traveling along its orbit.
Meaning, if a comet has rounded the sun and is heading back out into deep space, its tails are actually leading the way.
It's essentially flying through its own exhaust.
Yeah. It is so counterintuitive. But it's just pure physics.
It is.
Now, to understand where these bodies come from, we have to map the dynamical reservoirs. We hear the terms short-period and long-period comets a lot. Let's break those down.
Sure. So short-period comets generally take less than 200 years to complete an orbit around the sun.
Halley is your classic example there, right?
Exactly. Halley is the benchmark. Dynamically, these often originate from a region called the scattered disk. That's a chaotic area just beyond Neptune, intricately linked to the Kuiper belt. And the Kuiper belt is that massive, flattened ring of icy bodies out on the ecliptic edge of the planetary system.
Like where Pluto is.
Right, where Pluto is. But then you have the long-period comets. These are bodies that take thousands or even millions of years to make a single orbit. They drop in from wildly unpredictable angles. They'll plunge over the poles of the sun rather than traveling along the flat planetary plane.
And they come from the Oort cloud.
Yes, but we need to make a really crucial scientific distinction here. The Oort cloud is completely model dependent. It is a theoretical necessity, but we have never directly photographed or imaged the Oort cloud.
Oh, wait, so we've never actually seen it.
Never. We infer that it exists because we see these long-period comets dropping into the inner solar system from literally all directions. So the orbital math dictates there must be a massive spherical shell of icy debris surrounding us, stretching perhaps halfway to the nearest star.
That is mind-boggling.
Well,
Halfway to the nearest star. And just because a comet takes millions of years to arrive from the distant Oort cloud doesn't mean it's an interstellar visitor.
Right.
Because the term interstellar gets thrown around a lot in the press today. But most of these long-period comets are gravitationally bound to our sun.
Yes.
They belong to our solar system. They just live in the deepest, darkest suburbs.
Which is exactly why they are so scientifically prized. I mean, they've been out in the deep freeze, far away from the sun's altering heat, for billions of years. But this raises a really critical question about what scientists actually measure. What does the word primitive actually mean when we talk about studying these objects?
Because we set up that central tension earlier. We called them an edited archive.
Exactly. We have to rigorously test the assumption of what primitive means. There's a vast difference between a primitive archive and an unchanged object.
Right.
Yes, they retain isotopic information and building blocks from the early formation of the solar system, but a comet's surface is constantly being edited, even out in the deep freeze.
How so? If it's in the deep freeze, shouldn't it be perfectly preserved?
You would think so, but it's bombarded by high-energy cosmic rays for billions of years. That alters the top layers of the ice, and then, when it drops into the inner solar system, it goes through extreme thermal cycles. Gas drag alters its shape. The very act of a comet becoming active, sublimating ice, collapsing sinkholes, shooting out jets, all of that destroys its own physical context.
So the fundamental challenge for planetary science is, how do we actually read an archive that is constantly burning its own pages?
That is the perfect way to put it. And to do that, we rely on a ladder of inference. We gather data using very different observational methods, and we have to be honest about the limits of each one.
Okay, so let's walk through that ladder. What's the first step?
Well, take telescopes and spectroscopy. We can look at the light reflecting off a comet's coma, spread that light into a spectrum, and identify the chemical signatures of the gases present. That is incredibly powerful for studying huge populations of comets and finding patterns.
But there's a limit there, right? You're looking at the coma, not the solid nucleus.
Right. And the molecules in the coma have already been blasted by ultraviolet sunlight, so you're measuring daughter molecules that have been broken apart, not the parent molecules trapped safely in the ice.
Ah, I see. To use an analogy, it's like trying to reverse engineer a car's engine by only analyzing the exhaust fumes blowing out the tailpipe.
Exactly. To see the engine itself, we needed spacecraft. So in 1986, humanity sent the Halley fleet. This was an international armada of probes, including the European Space Agency's Giotto and the Soviet Vega missions, flying right through the coma of Halley's comet.
And they captured the very first images of a comet's nucleus.
Yes, finally proving that the dark, solid, active dirt ball was real. But a flyby is just a fleeting snapshot. I mean, you zip past at tens of thousands of miles an hour. You only see one hemisphere under one specific lighting condition for a matter of hours.
Which led the scientific community to design some truly transformative missions that completely rewrote the planetary science textbooks. Let's dig into NASA's Stardust mission to Comet Wild 2.
Oh, Stardust was an audacious piece of engineering. The goal was to actually fly through the coma of a comet, physically catch dust grains flying off the nucleus at hypervelocity speeds, and bring them back to Earth.
But how do you catch something moving that fast without just instantly vaporizing it on impact?
Well, engineers developed aerogel. It's this incredibly lightweight, porous silicon foam. It's mostly air, and it's designed to gently catch and slow the particles down, sort of like a bullet firing into snow.
And it worked. They brought those tiny microscopic grains back to the labs on Earth. But what they found under the microscopes broke everyone's models of how the solar system formed, didn't it?
It absolutely did.
But
They found high-temperature minerals. Specifically, they found calcium-aluminum-rich inclusions and olivine.
okay, wait. High temperature. Why is that a problem?
Because these are crystalline structures that can only form in incredibly hot environments. We are talking thousands of degrees, like the environment right next to the young, violently active early sun.
But they found them trapped inside a comet that definitively formed out in the freezing outer edges of the solar system.
Exactly. A frozen dirt ball from the edge of the solar system is carrying rocks forged in the absolute heat of the inner solar system.
That fundamentally alters the picture of our origins. I mean, how did it get out there?
It proved that the early protoplanetary disk wasn't just a static gradient where, heavy, hot rock stayed near the sun and cold ice formed on the outer edges. There was massive radial mixing. The early solar system was basically a churning, violent blender.
A blender, wow.
Material formed near the sun somehow migrated all the way out to the cold outer edges before being locked into these comets.
Okay, so Stardust brought a piece of a comet to us.
Yeah.
But then we had the Deep Impact mission, which basically brought the laboratory to Comet Temple 1. And when I say laboratory, I mean a massive 800-pound copper projectile.
Yes. Deep Impact was an active, controlled experiment. The logic was, if the surface of a comet is baked and weathered by the sun, let's essentially drop an impactor into the nucleus to blast away that weathered crust and expose the pristine material hiding underneath.
Why copper, though? Why not just a steel block?
Because they were looking for water and carbon. If they used a standard impactor, the materials in the probe might contaminate the spectral readings. Copper is inert for what they were looking for, so it wouldn't mess up the chemical signatures of the comet's plume.
Clever. So when that copper impactor hit, what did they see?
It revealed a highly porous, structurally weak surface concealing abundant water ice and complex carbon compounds.
But even that brilliant experiment has caveats. Because when you kinetically blast a crater into a comet at 23,000 miles per hour, the material that flies out into the plume isn't exactly pristine anymore, is it?
Not at all. An impact plume is a highly selective, altered sample. The sheer kinetic energy of the impact instantly heats the material. It sorts the particles by size, and it actually changes the chemical bonds before our instruments on the flyby spacecraft can even read the data.
So you aren't looking at an untouched, perfectly preserved core.
No, you're looking at the immediate aftermath of a localized violent event.
Which perfectly sets up the crown jewel of comet exploration, which is the Rosetta mission and the Philae lander at Comet 67P. Also affectionately known as Churyumov-Gerasimenko.
Yes.
This wasn't a fleeting flyby. This wasn't a kinetic strike. This is moving in together. Rosetta orbited the comet for over 2 years.
And living with a comet revolutionized our understanding. Because Rosetta stayed in orbit as 67P moved closer to the sun and then retreated, we actually got to watch the seasons change. We mapped the complex gravity field, we calculated the internal density, and we watched sinkholes collapse and jets intensify in real time.
We basically saw how the comet actively eroded and reshaped its own surface.
Yes.
And then there is the Philae lander, which, we have to admit, did not go according to the original engineering plan.
Oh, it was terrifying for the engineers.
When it touched down on the nucleus, the harpoons designed to anchor it into the ice completely failed to fire. And Philae bounced. In that incredibly low gravity, it literally bounced hundreds of meters across the surface of the comet for hours before finally wedging itself sideways under a dark cliff overhang.
The initial reaction in the control room was absolute dread. But the scientists quickly turned that engineering failure into an incredible scientific advantage.
How so?
By bouncing, Philae inadvertently gave us a multi-point surface measurement. Instead of just sampling one tiny localized landing zone, it touched down in multiple drastically different terrains. That gave us comparative data on the magnetic fields, the compressive strength of the crust, and the physical properties of the comet across a wide swath.
Now, I have to point out a potential trap here.
Yeah.
Rosetta gave us such incredibly high-definition, awe-inspiring photos of 67P. It has that very famous rubber duck shape.
Yes, the two lobes.
Right. 2 distinct rounded lobes stuck together by a narrow neck.
Mm-hmm.
And because we have such exquisite data on it, there's a strong temptation for the public, and honestly even some researchers, to look at 67P and say, so this is what a comet looks like. But generalizing all comets based on 67P would be a mistake.
It would be a catastrophic mistake for planetary science. 67P is what we call a contact binary. It's the result of 2 completely separate bodies that gently collided and stuck together early in the solar system's history, which is another consequence of that chaotic radial mixing we talked about earlier.
Right.
But if you look at the nuclei we visited, Temple 1, Wild 2, Halley, Borrelly, 67P, they show massive structural and chemical diversity. Some look like bowling pins, some look like weathered potatoes. You just cannot use one single comet as the universal template for the entire population.
So we've seen how these spacecraft-proved comets are chaotic, churning mixes of material with incredibly complex histories. And the moment scientists realized comets were actively carrying this complex mix of water and organics, it immediately ignited the biggest debate in planetary science.
The origins debate.
Yes, the origins debate. Whenever comets make the news, you see two massive definitive headlines. Comets brought Earth's water, and comets brought the building blocks of life. Let's tackle water first. Did comets fill Earth's oceans?
The scientific reality is we don't know. Anyone who presents that as a solved, definitive slogan is really ignoring the sheer complexity of the data. The origin of Earth's volatiles is a wide-open, fiercely debated scientific question.
So how do we even begin to investigate that? I mean,
Yeah.
you can't just look at a drop of ocean water and visually match it to a block of comet ice. What is the mechanism?
We use an isotopic signature, specifically the deuterium to hydrogen ratio, or DH ratio. So hydrogen is the most abundant element in the universe. But a small fraction of hydrogen atoms have an extra neutron, making them heavier. That heavy isotope is deuterium.
Okay.
So if the specific ratio of heavy water to regular water in a comet's ice matches the exact ratio found in Earth's oceans, it suggests a strong connection.
I was thinking of the DH ratio like a chemical fingerprint left at a crime scene.
I like that.
If you find a suspect's fingerprint at the scene, it proves they were compatible with the scene. It proves they were present in the room. But it doesn't prove they committed the entire crime single-handedly. Just because a comet's water fingerprint matches Earth's doesn't mean comets supplied all or even most of our water.
That analogy perfectly captures the limits of the evidence. A match proves compatibility, not exclusive contribution. And the actual data we've collected from comets is, well, it's a wild roller coaster.
Yeah, tell us about the Rosetta reversal.
Okay, so when the Rosetta spacecraft first measured the water outgassing around 67 the DH ratio was way off from Earth. It was about 3 times higher. The press releases immediately declared Jupiter family comets ruled out as the source of Earth's oceans.
But the scientific method is all about refinement, right?
Precisely. Years later, a deeper reanalysis of the Rosetta data showed that those initial readings were heavily biased. They were measuring water molecules interacting with local dust grains in the coma under specific temperature conditions near the spacecraft. When they modeled the gas sublimating directly from the pristine ice of the nucleus, the ratio actually appeared much closer to Earth's.
Oh, wow, so it flipped completely.
Pretty much. And to add even more complexity, we recently took spectroscopic measurements of a completely different comet, 12 Pons-Brooks, and it also showed an Earth-like DH ratio.
So comets are absolutely suspects in the lineup. But they aren't the only suspects in the room. We have asteroids, which are actually very strong contenders for delivering water.
Very strong.
We have inherited water that was just trapped deep inside the silicate rocks when Earth originally accreted. We have internal outgassing, where volcanoes release water vapor from the mantle. The reality is likely a very messy combination of all of these sources.
The early solar system was basically a chemical collision zone, and that exact same messiness applies to the other big headline, organics and life.
Yes, the building blocks of life headline. People read, scientists find organics on Comet, and their brains immediately jump to alien microbes hibernating in the ice. We need to rigorously define the word organic in this context.
Yes, we really do. In chemistry, organic simply means non-biological carbon chemistry. It refers to molecules that contain carbon bonds. It emphatically does not mean biological in origin.
Right.
You can easily form methanol, formaldehyde, and incredibly complex macromolecular carbon in the frigid, irradiated vacuum of space without any biology being involved whatsoever.
But the Rosetta mission did find glycine on 67P, and glycine is an amino acid. It is literally one of the structural building blocks of proteins in our own bodies.
Finding glycine is profound. It confirms that comets carry prebiotic ingredients. But as scientists, we have to vigorously separate direct observations from model-dependent interpretations.
Finding the ingredients for life is not finding life itself.
Exactly. If you walk into a forest and find a pile of lumber, some nails, and a hammer, you haven't found a house.
Right.
You've just found evidence that the raw materials to construct one exist in the environment.
So if we extrapolate that back to the Haiti eon, the early Earth is getting relentlessly bombarded by these comets and asteroids.
Yeah.
They're actively delivering these complex carbon molecules to the surface. But it's totally possible that the early Earth was already cooking up its own organics down in deep-sea hydrothermal vents or through atmospheric lightning strikes.
That is the leading edge of the debate. The delivery of extraterrestrial organics from comets and asteroids might have just enriched an already existing chemical network on the early Earth.
Like a supply drop.
Yes, it might have provided a helpful supply drop, rather than being the solitary magical spark that created life from nothing. The current evidence supports cometary contribution, not absolute necessity.
Which is a beautiful transition, actually, because if we are talking about comets delivering the building blocks of life through bombardment, we have to talk about the physical mechanics of those impacts.
We do, but we need to discuss impacts without the constant apocalyptic catastrophe framing that dominates the media. We have to view planetary impacts as a normal, ongoing mechanism of planetary evolution. It is a dual process of creation, delivering volatiles and mixing crusts and destruction.
I completely agree. We need to step away from the clickbait. The classic example everyone immediately points to is the Chicxulub impact that triggered the mass extinction of the non-avian dinosaurs 66 million years ago. But honestly, whether that specific impactor was a comet or an asteroid is still heavily debated in the literature.
It is.
A much better observed laboratory for impact physics was the Shoemaker-Levy 9 impact on Jupiter in 1994.
Oh, Shoemaker-Levy 9 was an astonishing event for planetary science. As the comet passed too close to Jupiter, the planet's immense tidal forces literally tore the fragile nucleus apart into a string of pearls, over 20 individual fragments.
And then, as the astronomical community watched in real time, they slammed into Jupiter's atmosphere one after another.
It was incredible. We watched massive, dark atmospheric scars form, some of them larger than the Earth itself. It proved definitively that these massive collisions aren't just ancient, abstract history from the Hadean Eon. They are a continuous, dynamic mechanism in our solar system today.
But witnessing that on Jupiter doesn't mean we need to panic every time a new comet makes the evening news. There is a massive fundamental difference between a comet's brightness and its danger to Earth.
Right. A spectacularly bright comet dominating the night sky does not equal a high-impact probability. It just means the comet's nucleus is highly active, outgassing massive amounts of dust and reflecting a ton of sunlight.
Risk assessment in planetary defense is a product of probability and consequence. The actual probability of a long-period comet striking Earth is incredibly infinitesimally low.
However, because they drop in from the deep Oort cloud at immense relative speeds, sometimes exceeding 100,000 miles per hour. Yeah, and because we often only spot them a few months before they cross Earth's orbit, the potential consequence is severe. That is why planetary defense treats cometary tracking as a serious, measured, and highly collaborative international responsibility.
And humanity is actively testing our capabilities. Everyone saw the headlines about NASA's DART mission, where we deliberately crashed a spacecraft into a space rock to measurably change its orbit.
Yes, the double asteroid redirection test.
But we need to be incredibly clear about the physics here. DART deflected an asteroid moonlet. It was a relatively dense, rocky body, deflecting a fragile, highly active, venting cometary nucleus that is held together by its own weak microgravity. That is a vastly different, far more complicated physics problem.
Absolutely. If you hit a highly porous comet with a kinetic impactor, you might not deflect it. You might just shatter it into a shotgun blast of debris heading on the exact same trajectory.
Which would be worse, honestly.
It would. It requires a completely different architectural approach to deflection and mitigation, which is why the future of this field is so deeply exciting. And we aren't just looking at the dynamics of our own solar system anymore. The frontier of cometary science has moved to exocomets.
Comets orbiting entirely different star systems.
Yes, but I want to be clear about the observational limits here, too. If you look at the young star Beta Pictoris, for example, we do not have beautiful, high-resolution photographs of little glowing comet tails zipping around that star.
Right, they're too small and far away.
Exactly. These exocomets are inferred. We detect them using the transit method. We watch for transient, irregular dimming of the starlight as the dusty comas pass in front of the star, casting a shadow.
So we look for dips in the starlight.
Yes. And we look for highly specific, changing absorption features in the star spectrum that tell us gas is sublimating.
It's like watching a faint wisp of smoke pass over a distant spotlight. But what that shadow tells us is profound. It means that this whole violent, beautiful process, icy bodies scattering around a young star, colliding, outgassing, delivering volatiles to inner rocky planets. It isn't just a localized quirk of our own solar system.
No, it is a common fundamental galactic mechanism for planetary evolution.
Which brings us back home to the ultimate question of planetary stewardship. How do we take all this knowledge, from historical omens to exocometary transits, and responsibly explore our own cometary neighbors in the coming decades?
Well, the next generation of missions sounds like something pulled straight from a science fiction novel.
It really does. Look at the European Space Agency's Comet Interceptor mission. Historically, we spot a comet, we spend 10 years building a probe, and we launch it, hoping the math aligns to catch it.
Right, the traditional chase.
But the interceptor uses a rapid response architecture. It is designed to launch and park itself in a stable Lagrange point in space. It just waits in the dark.
A comet ambush.
Exactly. When ground telescopes spot a dynamically new comet plunging in from the Oort cloud, or potentially even an interstellar object dropping into the inner solar system, the interceptor rapidly deploys to meet it, observing a completely unweathered surface before the sun has a chance to severely alter it.
It is a brilliant paradigm shift in exploration. But the absolute holy grail, the ultimate defining goal for planetary scientists working today is cryogenic sample return.
That is the dream scenario.
We talked earlier about Stardust returning those dry, refractory dust grains in aerogel. But imagine the engineering required to land a spacecraft on an active comet, drill deep beneath the weathered crust into the pristine primordial ice, seal that core sample in a cryogenic vault, and fly it all the way back to Earth without it ever melting, sublimating, or undergoing chemical alteration.
The engineering tolerances would be insane, and it would require massive, stringent planetary protection protocols, not because we expect to find living alien microbes in the ice, but because we need incredibly careful curation to ensure we don't contaminate the sample with Earth's own organics or isotopic signatures.
Exactly. We don't want to measure our own exhaust, basically. But if we could pull it off, it would be the first time humanity truly brought the unedited archive of the solar system into our terrestrial laboratories.
It would allow us to utilize instruments that are simply too massive and power-hungry to ever fly on a spacecraft.
It would finally let us answer those foundational questions about where our oceans and our prebiotic chemistry actually came from, with zero observational bias.
So if we synthesize everything we've talked about today, from Tycho Brahe mapping the sky to the comet interceptor waiting in the dark, the overarching narrative is clear. Comets aren't just celestial spectacles, they are magical omens, and they aren't just simple, dirty snowballs.
No.
They are the edited, highly dynamic archives of how solid worlds were built, how primordial materials were violently mixed, and how planetary bodies evolve over billions of years. They connect the deepest, most chaotic history of our planetary formation directly to our future scientific responsibility and stewardship in space.
They are the messy, active, and endlessly fascinating bridge between our cosmic origins and our destiny.
Before we wrap up, I need to share this exact notice with our listeners. This Cosmora HQ audio podcast is an independent book overview, not an official or complete audiobook. Please support the writers and publisher by accessing Comet through a library, bookseller, publisher, or authorized service.
Great!
We would absolutely love to hear your thoughts on this deep dive. Drop your comments below, and I want to leave you with this exact spoken question to mull over. If we could return one perfectly preserved sample from a comet, what should scientists test first?